joint method for marker-free alignment of tilt series in electron tomography.
Okay, I'm sorry. This. Okay. Oh yeah, it's okay. Hello, everyone. Today is my great honor to present our work here. Yeah. Today, my topic is related to the electron microscopy. And maybe something not so related to others' work. So I will first make a brief introduction to the to what is electron tomography. Currently there are people trying to predict the structures, but now people also try to see what it really is. So electron tomography is a technique that to obtain detailed 3D structures of subcellular molecular objects. It bridges the resolution gap between the light microscopy and the molecular imaging techniques like X-ray. Yeah. Here. For electron tomography, we may need 3 steps. First, we got a sample, and we rotate the sample and get a series of different projections with different tilt angles, and then we combine the information of different projections and got a 3D structure. Yeah, this is the workflow, and this is a schedule. It is indeed an inverse problem. Yeah. Related to what we should do is alignment and reconstructions. Alignment is to correct the parameters that used in photographing. Sometimes the machine will not be so robust. So if the machine not so robust, we may get miss parameters of the projections. So we should fix it. Then in the last, we should solve the inverse problem. From the 2D information, then we got the 3D informations. Today, my topic is focused on the alignment problems. So why we need alignment? Here is an example. Yeah. We know for ET, we get a series of projections. And if all the parameters are well calibrated, we will get an inverse problem be solved, and just like this. If the object is at 1 point, we get a series of projections, and then we solve the inverse problems, then we got 1 point. Yeah. However, if it is misaligned, we got a series of tail series. But we make the inverse problems in the wrong way, then we will get a point with artifacts. Yeah. So artifacts with degrees of resolutions. This is why we need alignment to fix the problems. For alignment in ET, there generally have 3 strategies. First is Fluidium mark-based alignment. We will put some gold beans on the samples, and we got a tail series with gold beans, and this bean can be used to check and alignment. And otherwise, we use the structure inside samples to we make cross creation of these projections, and then we try to calibrate the parameters. And for last, we may make some virtual markers. Yeah, it is related to both the cross creation and Fluidium markers. Yeah. Here, We will talk why the classical solution is not enough. For the let you see what the ET have done. We got a sample and we got projections in different directions. And for 2D projections, the 2D features will not indeed corresponding to the 3D structure. This is an example. We got a projection in this direction, and we got a function like this. But if we totally change the directors, we got a function like this. We cannot relate this to this. This is the problem. Why the 2D features or cross creation techniques will not be so will not work so good? Yeah, because the 2D will not necessarily corresponds to the 3D. Indeed, for the video mark-based alignment, it is currently the most accurate solution is here. We will think why it is the most accurate one. Yeah, there are two things. First, we get the God beams inside the samples. The God beams has dark density in the projections, and also it has a circle shape. It is a sphere, so we can get its center, and the center can be easily checked around the projections. So this is why people use fit markers. And the key is the 2D, 3D relationship between sample and its projections has been presented by the fit markers. Yeah. Now we come to our problems. If there are no fit markers, what we should do? We propose the joint element solution in ET. We start from an interesting observations. Yes. Here is a well-aligned, well-calibrated tilt series. And we try to get some small pitch, and we get the corresponding projections, local projections stacked into our tilt series. And finally, we found that it recomposes a small tilt series. So it can be said a global problem can be decomposed into several local problems. And we look back into its model. Yeah, if we write the original point into the classical projection model, we can get the local consistency of the projections. It is formulated that the system could be relocated to any origin point with such a translation that T applied to the projections, i.e., yeah, we got the local tilt series and then we reform them and they will become a tilt series that can be used for reconstructions. This is our observation, and from the observation, we design such a process. We decompose the whole problems to small ones, and from small ones, we got the virtual checks, and then from virtual checks, we come back to the global problems. Yeah, here is our total 4 steps. And for our algorithm, first, we try to find the local patches. We start from the view-to-view relationship between 2 projections. According to our most recent work, we found that 2 views of projections are related by the affine transforms we are within a tight bound. So, give 2 views. We can use some factual strategy to get the structures on the views and their corresponding relationships. And then by the corresponding relationships, we make robust estimations. Then we got finally affine relationship. From the affine relationship of the 2 views, we can by 2 views And as another two views, then we can got the appropriate relationship of the local patches. Then we got a series of local patches. We got a series of local tilt series. This local tilt series is not so exact. Is not so exactly solved. So we should resolve its parameters. And here we look better into the model, the projection model. But here we look into the voxels. This is a sample that we supposed it be. This is a sample we think it should be exactly what it is. And this is the projections. And we look into the tilt series. We should find that a pixel on the projection is an integral of the voxels in the samples. So we try to solve such reconstruction and reprojection problems. Our goal is to optimize the supposed samples and its reprojections and what we observed and make their difference, minimize their difference. And if we solve the local problems, then we substitute the local centers into the global ones, and we got a lot of local centers. And these local centers, we call them reproject invariant landmarkers, because according to the projection model, their centers should be exactly the tilt series' original center. Yeah. So we compose a series of virtual checks, and then we go back to the field markers projection model. We solve this model just like what a field mark-based element technique have done. Yeah. So with this, we can keep the 2D and 3D relationship. In our whole algorithm, we iterative to refine the local patches and the global check-based alignment, and then until they are converges. Because a local patch-based element is start from its intensity. It is intrinsic of the samples, and for the global element, it is based on the checks. So it is an extrinsic problem. It's a extrinsic solution. So it's indeed is a joint solution for the mark-free element. Yeah. So finally, we see how it works. We use 3 samples, filament, mitochondria, and physical to test our solutions. First, we try to see how the checks have been aligned. Here, we make an example from the filament dataset. The B is the landmarkers without element, and C and D are the landmarkers that they have been well aligned by our solutions. And for C, it is XY views. If the checks is horizontal enough, it is said that the tilt series has been aligned very well. Yeah, and for D, it's also, it has a very good checks, looks like just like a thin functions, it will be good. Yeah. We also compared our result by the reconstruction with the I mode and the most popular ones. Yeah. We can find that the reconstructions are almost the same with the classic solution. It is we use the I mode as a field mark-based element. Yeah. And we also compared our method with the classic feature-based element. For A is an old result of the 2013's feature-based element. A and B looks very similar. However, from C and D, we can find that we have much clearer membrane structures compared with the old feature-based element. That is to say, the depth information has been well collected by the joint element method. Yeah, here is another examples. Here also, we test the solutions on the visual data side and compared it with the causal cohesion-based method. The method, it is the classic method in mode. So, from the red arrows, we can find that our method has result much clearer viscous and membranes, and also the YZ sections. Also, by the FFC solutions, we have half an astronom's improvement. And by the leave one out analysis and the FFC curves, we also achieve much better than the classic solutions. Thus, we can conclude that by our joint method that the 2D and 3D relationship has been well discovered. And an intrinsic element and extrinsic could be integrated together to make the problem, to solve the problem better, yes. And we also think for a joint solution may become a uniform framework for the mark-free element in the field of electron tomography. Yeah, here, finished. And thank you for the collaboration of Professor Minxu and Professor Fa Zhang and for other collaborators. Okay, thank you. And thank you for our audience.
Questions at the end of a long day?
What's the minimum resolution of what you can?
What means the resolution?
In terms of nanometers or angstrom?
It's angstrom. Yeah. For electron tomography, its general resolution is around the nanometers. Yeah. Mm-hmm.
Thank you.
Okay.
So when you're going back from the local patches to the global patches, I was wondering if you're able to handle some inaccuracy in the goniometers. If you have slight translational movements or something, do you need to have really a single rotational axis? Do you assume that?
You mean single rotated axis? No,
the global rotation axis.
The axis. You talked about the axis. Yeah, we don't fix the axis. We just use the general projection models. Yeah, I know that usually people use a single rotated axis for the tilde series, but sometimes we can find that there will be pitch angles.
Okay,
yeah.
And this also incorporates general translational affine transformations?
We just start from this model. We don't fix the rotation angles. And however, in the local patch element and in the global element, their parameters are different. For local patches, we have omitted some parameters. For example, as you said, we use the single rotated angles because if too much angles, it is hard for optimization here.
Yeah.
And then in global, we can get the difference of different patches, and the different patches central could reflect the pitch angle or something else. So we can make an iterative optimization between global and local optimization to fix these problems. What you said, just what you said, it is single or it is not or something else.
Thank you.
Okay.
Okay, thank you very much. Thanks to Peter again.
Thank you.
So it's come to the end of another 3D SIG 2019. I personally would like to thank Rafi, who does the bulk of a large amount of work that goes into making this a success. So I want to thank you for that. And I'd also like to thank Charlotte Dean, who took over from me, so I didn't actually have to do anything this year. She's not here, unfortunately, but let's give her a round of applause in absentia. Rafi, you want to say a few closing words to this esteemed audience?
This year's program I felt was very, very strong. It was, I guess, this full integration with the ISMB may be working. And it was really hard to select the oral presentations from the posters. So yeah, keep doing that good work. I hope to see everyone and more in Montreal. So tell your colleagues that couldn't come here. And we still have a poster session today. So if you didn't have a chance to go check out the posters, keep going. So it's not a real end of 3D-SIG. We still have a poster session. But it's the same posters that were shown yesterday, so if you didn't have a time to catch everything, go today. And the last thing is that I made a call for volunteers to help make 3D-SIG relevant throughout the year earlier on, and I already got 2 volunteers for different things. One of the things that we will start is a monthly newsletter that will probably start with the highlights of the meeting. So if you have a particular talk that you really liked, that you took notes, not yours, please, that you want to contribute a paragraph about, we will then go on and select a few of these and put in this newsletter. We don't know yet where it will be published, in what format. If it will be indexed anyway, if it have a DOI or not. All of this is still in the air, but we want to make 3D-SIG relevant throughout the year. And one of the things that we decided to do, I didn't speak to you, Phil, but I assume you get your blessing. And we'll have several things in this newsletter, highlights of people's careers, of software, of interesting papers, and all of this has to be contributed by you. The least work I have on this is the best. But let's try to make this work. So do contribute whatever you felt was the best. And if you have anything that you didn't like in this meeting, things to improve, also write to me. And I hope to see you all next year in Montreal. Thank you very much.